Speaker is not working properly. Oh no. Yeah, I never did get the sound to come through here today. So I'm not sure if you guys can hear me. I believe you can. At the moment, I cannot hear y'all. So give me just 1 second. I'm gonna try changing to speakerphone. Let's try that one.
I can hear you.
I can hear you now too. That's wonderful. Alrighty. So the first thing I'd like to do today, I'm just going to spend a second here taking a quick peek at your homework. I believe I put some work problems in your homework set this week. But because I had to rush my son to the doctor on Monday, I haven't had the chance to meet with the person who's going to be delivering that lecture. That's our first student teaching day, actually, that lecture on work. So I may end up modifying this homework set just a tiny bit. I'll turn on the screen share here for a second. So the homework set I have open for you right now goes through section 6.4. Some of those problems towards the end are on this concept from physics called work. Work is basically the amount of energy you need to invest to move something. And that lecture was not going to be delivered by me, but by one of your classmates. Unfortunately, I haven't been able to invest the time with him to get things ready yet. So these last few problems, numbers 18, 19, 20, and 21, I may pull these off this homework set and move them to next week's homework. And in place of those, I would probably do section 7.1 on integration by parts this Friday, or maybe something else. I'll have to think about it a little bit. But today we're definitely doing more volumes, so let's get over to that. Turn off the screen share. Not new share.
Did you mean to say next Wednesday?
Oh, because next Monday is MLK's birthday, isn't it? Yeah. Okay, that would be next Wednesday then. All right. We'll figure out the details. But today, we know for sure what we're doing. Today, we're going to do more volumes.
We are mirror backwards on the screen, unfortunately.
I don't know why this thing defaults to that. I wish there was a way to change the default setting. Is that better?
Okay, yeah, it's all good.
Beautiful.
Thanks.
Yeah, of course, of course. Oh, and you guys can hear me, huh? Even without the lapel mic? I didn't realize I didn't put the thing on this morning. It's nice. All right, I won't mess with that. I might do 1 or 2 more examples from 6.2. So the focus is going to be on cylindrical shells, which is section 6.3. Let me pull up a copy of your book. Grab one quick problem from section 6.2 to work as sort of an introduction to this. Did I not save a copy here? I know I did. There it is. All right. So index on the left there. Okay, so that's this book. All right. Let's pick one that we could do either way. That would be fun. Did we do a problem on Monday about where we had to work with respect to the variable y, or did we do everything with
Yeah.
respect to the variable x?
No.
We got one where our strip was in horizontal. Okay, good.
I think you did that, yeah.
Okay, very, very good. See, we haven't had opportunity to do much with trigonometry yet. That's going to be. It'd be nice to do one about something like this. Okay, so let's take a look at this. This is a 6.2 exercise. We're going to work just kind of as a warm up, where the region isn't given to us in as clear terms as we might like. And that leaves us pondering, should we work with respect to the variable x with respect to the variable y? So I'm going to leave out a bunch of the words, right? Find the volume. Of the solid generated by rotating the region bounded by the curves. The curves are x times y equals 1, y equals 0, x equals y equals 1, y equals 0. Yeah, x equals 1, x equals 2, and we're rotating about the line x equals -1. Okay, so we've got 4 boundary curves. None of them looking quite like we're used to thinking of these curves as looking, with the exception of y equals 0. And then our axis of rotation is not one of the coordinate axes, right? This is a little bit strange too. We rotate about the x-axis, rotate about the y-axis. This is neither of those. So what we're going to do, always right, first thing you got to do is sketch the region. Sketch the curves, identify the region. X times y equals 1. This is the same as saying y is equal to 1 over x. And I know what that curve looks like, right? This is a unit hyperbola kind of rotated to the side. This is what 1 over x looks like in quadrant 1, and it's got a symmetric piece over here. There's some asymptotes that I'm not going to draw in because I don't want to clutter the picture if I can avoid it. So this is the curve x times y equals 1. Y equals 0, that's the x-axis. X equals 1 is a vertical line. All the points in the plane whose x coordinate is 1. And then x equals 2. Also a vertical line. All the points in the plane whose x coordinate is 2. These are our 4 boundary curves. Y equals 0 again is the x-axis. And so one boundary curve, another. So there is a region enclosed by these, right? We see it here. All the other regions are open. They can go on and on and on. Our region this fellow. And I want to rotate this about the line x equals -1. So first, I noticed that this part of the 1 over x or x times y equals 1 doesn't factor in. So I'm going to get him out of the way. -1. The line x equals -1 would be over here. And this is my axis of rotation. So we've got everything drawn. The scale is not unreasonable. This is actually a nice problem to set up for the transition from 6.2 to 6.3. This is a problem given in section 6.2, which is unfortunate because it's a problem that's much better solved using the methods of section 6.3. So what I'm going to do is I'm going to set this up with 6.2 and we'll kind of see why it sucks. And then we will set this up using the method of cylindrical shells from 6.3. If I'm going to use discs and washers, right? The technique that we've learned so far. We know that my next step is to draw a little differential thickness strip in that region at an arbitrary position. Should that strip go in oriented horizontally or vertically? Horizontally, right? Because it's always perpendicular to the axis of rotation. I'm going to draw it right here. But you'll see that there's kind of a bit of funny business here. Obviously, if I rotate that strip, I will generate a washer-shaped solid. Oriented something like this. Whose thickness here would be a dy thickness, right? The thickness of the strip is a vertical thickness, it's a small change in y. And it has two radii, a little inner radius and a larger outer radius. And the volume of the little purple washer I call dV. We know dV is pi times the outer radius squared minus the inner radius squared, in this case, times dy, because the thickness is a little y thickness. So what I need to do is find that inner radius and outer radius as functions of the variable y. I want you to stare at the sketch for a second, the graph sketch, and try to see why that's a little strange. Anybody tell me something a little bit strange about finding, say, the outer radius as a function of y? Certainly, it's going to change. Yeah, it's not constant. And more than being non-constant, it kind of depends. Even the function itself, big R, is going to be a different function if we're down here than if we're up here, right? If I'm down below this point, if my strip is down here, then big R is constant, right? It's this distance, and it's that same distance everywhere through here. But as soon as I get above this intersection point, big R starts to shrink in. So in other words, we need casework. Big R is a different function below the intersection point that I've labeled there. Point down above. Right below this intersection point, big R is constant. It's the distance from -1 out to 2, which is 3. Above this point, it's variable, right? As I move vertically through this region here, big R is going to shrink. First, let's find this intersection point. What is this? Well, this is where the line x equals 2 hits the curve y equals 1 over x. So, intersection point. So 1 over x hits the line x equals 2. Oh, that's not. Oh, this is where xy equals 1. It's x equals 2. So if I want to find that point, I just plug 2 in for x here. Which would mean y is 1/2. The x coordinate there obviously is 2. That's the point. 2, 1/2. Box that instead. Right. So beneath this point, big R is constant. Above this point, big R is variable. Little r is always constant, right? Little r is this distance always, which is 3, right? The distance from near end of the strip to the axis of rotation. Two. And then big R is a piecewise function. Somewhere. So if y is larger than 1/2, if I am above this point, then big R is the variable function that gives me the distance from here to here. We'll just split this into two cases. We'll say if y is smaller than 1/2 and y is larger than 1/2. You could put the or equals to on either of those inequalities because one point doesn't change the value of the integral that we're going to set up. So just to make life simpler, let's include the 1/2 in this part because this is going to be the constant part. So if y is below this point, if my strip is below this point, then big R is the constant function 3. Right, it's the distance from here to here. Right, the vertical line x equals -1, the vertical line x equals 2, that distance is 3. Otherwise, we should do the thing where you characterize a point on this curve. And we need to do it in terms of the variable y. Right, so rather than thinking of this as x comma 1 over x, which I could do, you could also think of this as solve for x here, you get x equals 1 over y. So I can think of this as the point 1 over y comma y. Right, everybody, is everybody comfortable with what I'm doing when I do that? Right, if this is the function that we normally think was y equals f of x, I'm going to pan the camera over for you guys in just a second. So when I do this thing where I say we're going to characterize a point on the curve, it's very important you understand what I'm talking about. I'm getting some stuff in chat here. Wicked blurry. Okay, better. Okay. So when I say that I want to characterize a point on the curve, right, if this is the graph of the function f of x, in pre-calculus you learn that every point on that curve is of the form x comma f of x. Right, so one way I could characterize the point on the curve y equals 1 over x is x comma 1 over x. You could also call this is the same thing as saying inverse of y comma y. Ringing any bells? All right, like I want to talk about y equals x squared. The point on this curve is x comma x squared. But I could also call that the square root of y comma y. The same thing. But that's what I'm doing over here. You need this every time you do one of these problems and you set up the integral with respect to y or with respect to you have to change the
Does I haven't seen that in a while. Is the f -1 inverse? Or?
Yeah, inverse function. Yeah. So basically you just go to the equation that gives you the curve, like here xy equals 1, and solve for one variable or the other. If I solve this for y, I get y equals 1 over x. So I can think of this point here as x comma 1 over x. If I solve it for x, I get 1 over y. So I can think of it as 1 over y comma y. Okay. What we're trying to do is find out what big R is if y is beneath this intersection point. If my strip is above this intersection. We said that this point on the curve can be thought of as 1 over y comma y. So big R is this horizontal distance. It's the x value here minus the x value here. The x value here is 1 over y. The x value over here is -1. So this is 1 over y plus 1. Right, minus -1. In other words, we need two integrals. Right, I need one integral that works while the strip is down here, and I need one integral that works while the strip is up here. Bring pan over. The volume is the integral of the little differential volume taken from the smallest y value in this region up to the largest y value in this region. Smallest y value in this region down here is y equals 0. Largest y value in this region is the y value at this point right here where 1 over x hits the curve x equals 1. That's 1. The integral from 0 to 1 of dv, and those are y values. And unfortunately, dv is a different function depending on whether y is bigger or smaller than 1/2. All right, so we need to do two separate integrals. My first step would be to split this up as the integral from 0 to 1/2 dv plus integral from 1/2 to 1 dv. Because capital R is different based on whether y is bigger or smaller than 1/2. That means dv is different based on whether r is bigger or y is bigger or smaller than 1/2. From 0 to 1/2, when we're talking about y values that are smaller than 1/2, capital R is constant. So this would be pi times cap R squared, that's 3 squared, minus little r squared. Little r, right? Little r really is constant because R is 2. So 3 squared minus 2 squared. That's modified integral dy. Plus the second integral, the integral from 1/2 to 1. This is the slightly trickier one here. Little r is still 2, but big R is 1 over y plus 1. This is pi plus 1 squared minus 2 r squared dy. Neither of these is like a really hard integral, but none of them are fun. This is the integral of a constant, right? This is 9 minus 4 is 5. Integral 0 to 1/2 dy. Over here, I can pop the pi out. Integral 1/2 to 1. 1 over y plus 1 squared minus 4 dy. If it's okay with you, I'm just going to focus on this guy for a minute. Integral 5 pi dy. We'll write it. 5 pi, the antiderivative of just dy, that's y. We evaluate that from 0 to 1/2. And then plus this thing, which I will take to the side over here. And from 1/2 to 1. Pi out front. One over y plus 1 squared minus 4 dy. Need to FOIL out the 1 over y plus 1 squared. So 1 over y squared is 1 over y squared. And then plus 2 copies of this times this is plus 2 over y. 2 times 1 over y. Oh, that's 2 over y. Oh, actually. Yeah, 2 times 1 over y. That plus 1 squared is 1 minus 4 multiplying of that first piece. And then 1 minus 4 is -3. An antiderivative, so 1 over y squared, you might want to think about, maybe write this piece of y to the -2. Everything's in a form you can see your antiderivative maximum simply. Power rule, natural law, power rule, right? So the antiderivative for y to the -2 is negative y to the -1 on -1 over y plus 2 times antiderivative to 1 over y is the natural log of the absolute value of y minus 3. And we give you a 3y. And we're integrating dy, so the constants give you y. And we evaluate from 1/2 up to 1. So this goes here. I'm going to erase this in a second. So are there any questions on these steps here? I'll give you guys just a second to write. Get some coffee. Questions on the far right column? Okay. Yeah. Sure. Right. Then we're ready to evaluate here. When you plug in 0, you get nada. When you plug in 1/2, you get 5 pi over 2. Here, when you plug in either thing, you're going to get some stuff, so we need to be a little bit careful. Open the big bracket. When we evaluate the upper bound 1, we get -1 for the first piece, plus 2 times the natural log of 1, minus 3. And then when I evaluate at the bottom end, minus. Plugging 1/2 in here, -1 divided by 1/2 is -2. Plus 2 times the natural log of 1/2. Minus 3 times 1/2. 3 times. What is the natural log of 1?
2.
0.
And looking at the other pieces here, I've got a -1 minus 3 is -4. Altogether here we have 5 pi over 2 plus -1 minus 3 is -4 minus -2 minus 3/2. Let's see, so this is -4/2. Yeah, -4/2 minus 3/2 is -7/2. Plus 2 times the natural log of 1/2. Looks good so far. pushing up here, that's 5 pi over 2. Plus 5 pi. 4 as a ratio over 2 is 8. So negative 8 halves plus 7 halves. And distributing this negative. Negative 8 halves minus 7 halves is negative 8 halves plus 7 halves is negative 1 half. And distributing this negative here, we have minus 2 times the natural log of 1 half. And you might ask, can I clean this up a little bit more? There's one thing, so first, so give me this for Gucci. Give me this for Gucci. Oh, with the fixed delimiter, right? Didn't I? Yeah, I need another. That's fine. Okay, this is fine. This is not fine, right? If you don't tell me that the natural log of 1 is 0, then take off a half point. Make sure you do that. Otherwise, the previous line would be an acceptable final answer too. With the purple, previous line is acceptable answer also. The one thing I would like to do here to make this a little more aesthetically pleasing, a negative natural log of 1 half, like that. Right, constant multiples out front can come inside. So the natural log of 2 is a nice number, right? Like it shows up all the time. It's like 0.69. You can remember that because everybody loves those 2 digits next to each other. But nobody knows what the natural log of 1 half is. So rather than a negative natural log of 1 half, I'd like to rewrite that as.
Does that work even if it's absolute value inside the natural log?
It does. Yeah, any constant multiple in front of the log, regardless of the base or whatever else is going on, can come inside the log as a power. So I'll distribute the pi.
Oh, thank you.
Minus pi over 2, and then plus 2 pi natural log of 2. I think this is more appealing. So the 2 won't be back here, but this negative I'm going to tuck inside to make the 1 half of 2, and then I'm also distributing the pi. And then of course 5 pi over 2 minus pi over 2 is 4 pi over 2 is 2 pi. This is 2 pi plus 2 pi times the natural log of 2. One of the things that's appealing about getting it down to this form at this stage, not entirely clear that this is even a positive number, right? One of the things I like to do when I calculate a volume is get the answer to a place where I can at least see it's positive, because if I get a negative number out for a volume, I know I made a mistake. And like I said, yeah, if you give me this, I will give you full credit. But I don't know, if you're out there working on something, would you rather work with this or with this? I would rather work with this.
How did you do that ln thing where you made it 2 then?
So I'm doing here the negative 2 ln of 1 half. That's the same as 2 times negative ln of 1 half. I'm just leaving the 2 out, we'll bring the negative in. And that's 2 times the ln of 1 half to the negative first power.
It's the negative.
And that's 2 times the natural log of 2.
Yeah,
So it's this rule.
first I thought you squared it. I was thinking,
Oh, no, that would be weird. So the general rule here is that if you have some constant out front, then this would be the natural log of a to that power. Multiples out front, logs can be set as powers. Okay, so I'm happy with this answer. It's pretty, it's obviously positive, but I'm really not happy with this procedure, right? Fuck this noise. This is a mess. I don't want to do 2 different integrals. I don't want to have to do all this garbage. So let's not do that garbage. The thing that made this hard is that your capital R is a piecewise function of y. If I rotate this strip so that it is parallel to the axis of rotation rather than perpendicular to the axis of rotation, then no longer do I have this weirdness where I step.
We
It's
can't
like
see the screen.
Oh yeah, sorry.
No worries.
All right, so this sucks because capital R is a piecewise function of y, right? We've got like some moderately reasonable behavior in here. Strip is acting okay, acting okay, acting okay, and then ka-chunk, it changes its behavior, right? And down below here, the radii behave very differently than they do up here. So if I were to rotate my strip so that it were parallel to the axis of rotation rather than perpendicular to the axis of rotation, as that strip moves through this region, there is no like ka-chunk point where the strip's dimensions suddenly change. I mean, they'll be changing, of course, as the strip moves through here, but they'll be changing according to the same rules rather than at this orientation as it passes over this point, it goes from having some variable capital R to a constant capital R. So the big insight here is that instead of leaving your strip perpendicular to the axis of rotation, you can set up your strip parallel to the axis of rotation. And that's the big difference between 6.2 and 6.3. Having the strip be parallel to the axis of rotation yields a different shaped differential solid, right? The DV, the little washer shaped solid we have here, is washer shaped because that strip is perpendicular to the axis of rotation, right? You revolve something that is perpendicular to this axis, it's going to sweep out a washer shape. If you revolve something parallel to this axis, it's going to give you a different shape. So let me, I'm going to come back and solve this problem a different way. But before I do that, let me just describe to you the method that we're going to use. I'll leave this up. It's really everything. So triangle strip. Triangle strip parallel versus perpendicular to the axis of rotation. If you draw the strip perpendicular to the axis of rotation, right? So with my axis of rotation, I don't really give a shit about what else is going on here. I'm just going to think about the axis of rotation in the strip. If I revolve this strip about this axis, I will get the washer shape that we've become accustomed to seeing here, right? And that means your dV is pi times big radius squared minus little radius squared times dt. Or dt could be dx or dy, depending on the strip. If I get my strip to be parallel to the axis of rotation, and I revolve that, I do get a pretty different looking solid. The solid here looks like a cylinder, but not the whole cylinder. It's like a cylinder with all the middle removed. Remember, this thickness here is extremely narrow, right? Called dx or dy, it's extremely narrow. Think of this like a soda can, right? Or like a soup can with the tops and bottoms removed. It's a cylinder, but it's like just the shell. Hence the term cylindrical shell, right? This is like a washer up here. And if cylindrical shell. I think of it like a soup can, a can of tomatoes, whatever. An extremely thin-walled cylinder with the middle all gone. We know how to find the volume of this thing. We talked about that, right? Think about the big disc, the little disc punched out. We find the volume of this thing. I'm adding the symbols perp and parallel here. So, anybody help me figure out the volume of this bad boy? So this guy, we had the two radii, right? Little r and big R, and this thickness here. Which I call dt. I guess I'll call it dt here because dt could be dx or dy depending on the context. What dimensions of that cylindrical shell are important besides the wall thickness, dt?
Height.
Certainly this height matters, yeah. The other thing, it's a radius, right? If you're looking straight down from above, it looks like a little annulus, a little ring. The trick to finding the volume of this cylindrical shell is to imagine cutting and unrolling. Right, so imagine I take some very sharp scissors, right, like my soup can. I've got some like poultry scissors or whatever. I cut it and I unroll my soup can. What I'm going to get then is like a sheet. It does have some thickness to it. It's extremely narrow, but it does have some thickness to it. So it's really kind of like a rectangular prism, parallelepiped. This thickness is still what we're calling dt, could be dx or dy, depending on the orientation of the axis. The height is still the height. What about this dimension?
Circumference.
Yeah, very good.
Would that
It's
be diameter?
this ring, which is 2 pi times that radius. So the volume of my cylindrical shell is the volume of this rectangular prism, because they're the same thing. I just cut and unroll the shell to get this. So dV here is just, length times width times height. That's 2 pi r h dV. And these pictures on the right here, this is like everything you need from 6.2, everything you need from 6.3, if you understand what's going on. 6.2, whether you're talking about a disk or a washer, really leans on this formula, because it's always this picture. If you have a disk, it's just a little r is 0. The only difference is strip perpendicular to the axis of rotation, strip parallel to the axis of rotation. In 6.3, you'll always be drawing your strips parallel to the axis of rotation, because that's how you generate a cylindrical shell. You don't have to always draw this picture and this picture. You just remember that the volume of a cylindrical shell like this is 2 pi times that radius times that height times that thickness. All right, with that in mind, let's come back and address the problem we flunked and hacked our way through with the dishwasher method and see if we get the same thing. All right, so this is the curve x times y equals 1, which we said is the same as y equals 1 over x. This is x equals 1, this is x equals 2, and my axis of rotation is x equals -1. The region is still the region we identified before. This region. If I'm going to do the cylindrical shells method, again, the only real difference as far as the picture setup is concerned, you draw your strip parallel to the axis of rotation instead of perpendicular. And here that makes life much nicer for us. Because now one rule will tell me the dimensions of the strip instead of needing like separate rules depending on where we are. If I rotate just that strip, I will get a little cylindrical shell. I'll draw it for you here. It's actually not that little. It's quite large in this case. Wide and that. Something like this, right? If I rotate this strip about this axis. Okay, the wall thickness here is this thickness is a dx. This time it could be a dy, right? If everything is turned sideways.
The drawing looks like you turned the slice sideways. Is it supposed to, or am I just seeing it wrong?
So I want to make sure I understand. So my axis of rotation is here and my strip is here. So I rotate this strip around this axis of rotation. So the big difference from
Oh, okay, I see it now.
parallel to the axis of rotation rather than perpendicular. So we should be getting a shape like this rather than a shape like this. You can't see the other board.
Cool, thank you.
We know that the volume of this cylindrical shell is 2 pi times the radius times the height times the little differential thickness, which is dx. That radius, I can extend my axis of rotation through here. The radius in the dv picture here is this, right? And the height is this. But really the trick is to label those things up here, because this is where we can figure them out. So my height is this, and my radius is this. All right, compare the picture above to the picture below. Again, characterizing the point on the curve where the strip touches the curve is kind of the game. And this time, since I know this thickness is a dx thickness, I don't have to work with respect to the variable y. I can keep everything in terms of the variable x. That's nice. The point along the curve y equals 1 over x is of the form x comma 1 over x. What is my height?
1 over x.
Very good. The height is the vertical distance from here to here. It's the length of the strip, right? So along this curve, the y value is 1 over x. At the base of the strip, the y value is 0. So the height is 1 over x. What is the radius? What is the distance from the axis of rotation to the strip?
One plus x.
Very good. All right, this distance, the horizontal distance from the y-axis to this point is just x, right? And this distance is 1. Or if you like, you can think of this as x minus -1. Just subtract the x values here and here. Right, that's x plus 1 like that. So now my differential volume dV is 2 pi times 1 plus x times 1 over x dx. So that's what we have to integrate to get our volume. And here, in order to think of the strip as kind of moving through this region, x just has to run from 1 to 2. The setup is so much simpler. So my volume here is the integral from x equals 1 to x equals 2 of dV, which is the integral from 1 to 2 of 2 pi times x plus 1 times 1 over x dx, right? The radius is x plus 1, the height is 1 over x. I can bring the 2 pi out. Distribute the 1 over x, so that's x times 1 over x plus 1 times 1 over x is 1 plus 1 over x dx. You see, this is going to give us this, and it's going to give it to us a lot nicer. It's 2 pi, and then your antiderivative of 1 dx is x, antiderivative of 1 over x dx is the natural log of the absolute value of x. And we divide it from 1 to 2. That's 2 pi. And then at the upper bound, I have 2 plus the natural log of 2. Minus at the lower bound, 1 plus the natural log of 1. Again, the natural log of 1 is 0. So this is 2 pi times 2 plus the natural log of 2 minus 1 of 2 pi times 1 plus the natural log of 2, which is 2 pi plus 2 pi times the natural log of 2, which is what we got before. But instead of needing 2 boards and some erased portion, when we calculate, I can get it all at half of 1 board. Because it's the better method. Cylindrical shells are your friend. Right, cylindrical shells are your friend anytime you can use them. And as far as I know, anytime you can use disk washer, you can use cylindrical shells. But there are problems where you cannot use disk washer and must use cylindrical shells. Now, I could be wrong about that. I'm just saying, so far I haven't encountered a problem that I can set up with disk washer method that I cannot set up with cylindrical shells. But I have many problems that I can set up with the shells method that I cannot set up with the disk washer method.
Isn't the disk washer just like a cylinder still? I mean, isn't that technically?
I get what you're saying, right? Yeah, if I were to squish this down and make DT really fat, these are kind of the same shape. But the idea here is that whatever is labeled with the DT should be thought of as infinitely small. So this one is infinitely short and has a really, really fat, like annular radius. This one is really tall and has an infinitely small annular radius. So, well, yeah, geometrically, they're the same thing. One dimension is exaggerated in the one and very, very small in the other.
So then, couldn't I use that 2 pi r HDT formula for the other one, the disk washer?
No, because when I say that my radius here is r, I'm actually kind of hiding something.
I can't see whatever's happening.
Yeah, sorry, let me bring the camera over so you guys can see. So this is a good question. So in the disk washer method above, it wouldn't make sense to say that there's one radius for this object, right? There's a fat difference between little r and big R here.
And the other one, there's not that much of a difference.
Right, because the wall thickness here is like infinitely narrow, there is not a fat difference between the inner and the outer radius. It's so close that we can get away with just saying it's the rate 1 radius, right? They're off by an infinitely small difference. But here, if you take this to be infinitely small, then the whole thing goes to 0. All right, if you take big R and little r to be equal, like we're doing here, this whole thing goes to 0. So we really do need to treat them as separate methods.
So then with the bottom one, is that like not like pinpoint exactly correct because we're just treating it as the same radius.
The truth is, there's a dirty truth underlying everything we're going to do in this class and everything we did in Calc 1. This is an old adage. Right? So in algebra, and by algebra I mean abstract algebra, like study of mathematical structure, we care very much about equality and exactness. And analysis, which is the grown-up version of calculus, it's all about inequalities. These are all estimates. They're all estimates. None of this is perfect. And the idea is that somehow through the limiting process, right, somehow by passing from this logic, which is really Riemann sum logic, right? What I'm doing here is I'm bullshitting you a little bit. This should be a delta. This should be a delta. Because there is an actual finite difference between those two. I'm drawing it as though it has a height. If it were a D rather than a delta, it would be too narrow for us to see. If you construct the associated Riemann sums for these, and then take the limit as n goes to infinity, allowing the delta to pass to a D, then you get the exact answer. But the logic that we're applying in these pictures to come up with these formulas is really delta logic. So think of these as like your Riemann rectangles. So the Riemann sums don't give you the exact area under the curve, but they allow you to understand how to build the integral, which as a limiting process does give you the exact area under the curve. These sort of Riemann disk washer or Riemann cylindrical shells would not give us the exact answer, but they allow us to set up the integral, which as a limiting process does give us the exact answer. In other words, we're estimating here, and then we're letting the integral pass to the exact answer for us. But don't tell anybody I told you. They'll be angry. Especially physicists. They do this shit all the time. Used to bug the shit out of me as an undergrad. I remember being like, no, that's not right. You're full of shit. Well, you can't call that a DT. I wouldn't be able to see it. They'd be like, shut up. It works. But if you want to look at the details of those things, you can get into the delta epsilon stuff, right? And it really does work. You just have to do a lot of inequality stuff and then send epsilon to 0. Okay, so that's one cylindrical shells problem. What am I doing on time? 10:19. Anybody ever seen the curved sine of x squared? A bit of a weird one.
Is this like one of the ones where as it approaches 0, you can see it, but then as it goes away, it's like really fast?
That's the idea. Yeah, near 0, x squared is not huge, right? And it's not growing especially quickly. But as x gets large, x squared goes faster and faster and faster, which is going to mean that this sine function oscillates faster and faster and faster the further you get from the origin. This is going to be, of course, as an even function now. I'll draw 2 sketches of this, one to kind of illustrate what you're saying, and then another. It's going to do something like this. As x gets larger and larger, x squared grows faster and faster. And you can think about that as like the frequency for the sine wave getting larger and larger, right? Meaning that the wavelength gets smaller and smaller. But near 0, it's going to be pretty well behaved. You know, some shit like this, right? I bring this up only because I want to look at this portion. So I'm going to redraw this. Volume. also lets me involve one of my favorite numbers, the square root of pi. So if I look just from, like just over the first little bit of this guy's life, this is root pi. How do I just mark this as root pi? Ignore the rest of the curve, there's all sorts of other stuff, whatever, I don't care. And 0 versus here. I like this as an example to illustrate when you should use one method over the other. The disk washer method has the advantage that it's easier to think of a solid as layers of disks and washers. Right? The cylindrical shells method, it's a little bit harder to think of the total solid as being a stacked up nesting of cylindrical shells. I don't know if anybody has looked at the resources I posted to Canvas and stuff. If I wanted to set this up using the disk washer method, don't write down what I'm about to do, right? Everything here you can put down. What I'm about to do, do not write down. If I wanted to set this up using the disk washer method, I would need to draw my strip in like this. And my inner radius would be here. And my outer radius would be here. Several problems with this. One, this is now a dy thickness, right? Means I need to solve this for x. I need to write everything in terms of y. Like that. You can do it, but the very first step is to take the inverse sine of both sides. And this comes with some restrictions, right? I cannot take the inverse sine of whatever I want. The sine, when we invert the sine function, we restrict the domain of the original to negative pi over 2 to pi over 2. And that means that the domain of this guy is restricted from negative pi over 2 to pi over 2. Well, guess what? Square root of pi is too damn big for that. This only works up to here. It doesn't work past there. And then things get fuckier. So this bad for us. It gets worse too, because then you take a square and you get plus and minus. Sine inverse y x. Does anybody know how to integrate this? No, fuck no. No, 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 no. No, even without this, no. Just no, please no. So, for many, many reasons. First off, you'll never be able to describe this point. You'll never be able to get capital R unless you play some very careful symmetry games. It can be done. I once had a Calc 2 student who just bugged me about it and was like, can you? So I was like, okay, yes, it is possible, but it's incredibly hard work. You have to use a lot of careful symmetry arguments and split it up here, and then it's not fun otherwise. It's really, really bad. And then the other thing is, even if you do all that, the integral you're going to set up is literally impossible. You guys may remember at the end of Calc 1, sometimes you have this conversation, you're like, okay, these functions we know how to find antiderivatives for. These functions we don't know yet, but we're going to learn in Calc 2. These functions nobody can find an antiderivative for. There's lots of them, e to the x squared, 1 over natural log of x, they just don't exist. This yields one of those if you set it up that way. So no disk washer. In fact, anytime your region is bounded by a single curve that is not one-to-one, right? The issue with that first step where you take sine inverse of both sides, I'm assuming that the sine function is one-to-one when I employ its inverse, but the sine function is not one-to-one. This curve is not one-to-one, right? It fails the horizontal line test. Anytime your region is bounded by a single curve which is not one-to-one, the disk washer method is bad news. because you won't be able to describe this point and this point separately from one another. At best, you'd get an integral that you could solve numerically from the dishwasher method. However, if you set this up with the Shells method, it comes very naturally. That's awful thick for a dx thickness strip, but it works. That thickness is dx. This point on the curve here, where the strip touches the curve, is x comma sine of x squared. Means that my radius is always the distance from the strip to the axis of rotation, and my height is this. So my dV here is 2 pi RH dx because that strip is a dx thickness strip. My radius is the distance from here to here, right? The horizontal distance from my axis of rotation to the strip. The x value here is 0. The x value here is x. So r is just x. The height is the y value here minus the y value here, which is sine of x squared. So not only is this setup much easier, but the integral you get from it is manageable as well. B here would be the integral from 0 to the square root of pi. 2 pi times the radius, which is x, times the height, which is the sine of x squared, and the thickness, which is dx. And yeah, this is not a bad integral. Anybody help me with this? I'm going to pop out the 2 pi. I'll be left with integral 0 to 2 pi x times the sine of x squared dx. Think back to last week's homework.
Is there z substitution for the x squared?
Indeed. Yeah, a little sub.
Did you say Z substitution or U?
You could use whatever letter you want. I've gotten in the habit of using the letter Z because in section 7.1, we're going to use the letter U, lowercase u, to mean something very specific. So Z sub or U sub, whatever you want to call it. We make a substitution. You're going to sub for the inner function here. And it's a nice move because dz is 2x dx, and I have an x dx here. I also need to change my bounds. When x is equal to 0, z is equal to 0 squared.
0 to pi.
And when x is equal to the square root of pi, z is equal to the square root of pi squared, which is pi. The integral becomes much nicer. Now just 0 to pi rather than 0 to root pi. X dx is 1/2 dz. This is going to be sine of z times 1/2 dz, right? And the idea that 1/2 dz is x dx. So I think that's this just giving me the 1/2 dz. And then even if it's left over is sine of x squared, that is sine z. So the 1/2 comes out, kills the 2 here. And then an antiderivative for sine z dz is negative cos z. I evaluate at pi, the cosine of pi is -1. If I evaluate at 0, the cosine of 0 is +1. Maybe I'll continue this. Here, this is pi times negative cos of pi minus negative cos of 0, which is pi times -1 is 1 minus negative, and then cos of 0 is 1. So once this is 2 pi. Right? So if you set this up with the dishwashing method, you will have a bit and a half even writing down an integral, because you've got to make all sorts of weird games to find your capital R with a function that is so not one-to-one and so restrictive. You set it up successfully, you power through that somehow. The integral you get is totally unmanageable. It literally cannot be done. If you set it up with the cylindrical shells method, the setup goes very smoothly, and the integral you get is a simple use of. Some problems, dishwasher will yield an easier. One of my favorite examples of that is if you take the natural log function from like 1 to e and revolve it around any vertical line on that region, is going to require integration by parts if you want to find the volume using the shells method. Straightforward use of exponential integrals if you use the dishwasher method. All right, before I let you go, we've got just a few seconds left. Before I let you go, I want to show you. Let me try. I want to show you how you can visualize these things. I think it's very easy to get sort of lost in the calculations. Oh my gosh, wait until I'm done teaching.
Could you pan us left?
I'm sorry, say that again.
Could you pan us left? Are you using the board on the left?
No, not yet. I am gonna
Oh,
share
no worries then.
in just a second. So here we go. All right. So if you come into the module section for our course, I can turn on the front screen. That's the other thing I meant to do. Sorry. Computer. Main projector.
One or something else. The quickest way, although
Sorry.
is to kill a healthy undead. And
Shush. Yeah, watching Sekiro videos while I uploaded this lecture from yesterday. Here we go. Okay. So if you come to the volumes of solids resources in the modules, I have a few videos and I just want to share with you a little bit here.
The volume of the solid formed by rotating about the y-axis. Now, for y equals x squared, y equals square root of x. And so we're going to take this region here and rotate it around the y-axis this time. And we're going to go ahead and slice vertically here. So we could, if we really wanted to, could change the problem to be a horizontal slice and use washers again. We're going to go ahead and try a different technique here and take this small slice and vertical slice and rotate it horizontally. Get an idea what happens here. There's our curve, there's our slice. And if we start revolving it, notice we get a different shape than we did before. Before we got a flat washer, here we're getting sort of a thin shell. And so this is called shells or cylindrical shell method. If we take a whole bunch of these shells now and a whole bunch of slices and revolve them all, you'll see how those little cylindrical shells sort of stack up to form the volume, right? And then in the limit, it would give the actual volume.
And that's that approximate to equal.
Okay, so let's see if we can figure out how to set this one up. So given an x value here, we know that this y value.
I'm not going to bore you with the setup here. So it's kind of tough, I think, sometimes to think about your solid as coming from these little dV solids, but that really is the game. Here's the one for disk washer, and I think people generally have an easier time visualizing this. Speed them up a little bit.
So here's my y equals x squared and my y equals square root of x. There is a representative for a slice. happens, that's going to give us this donut shape, well, washer shape is what we call it. It's a large circle with a hole in it, right? And for each slice of this curve, we will get a rotated washer. And if we get a whole bunch of those, right, we get a whole bunch of those little slices and we rotate them all, then we're going to get our actual shape, or at least a good approximation of it. In the long run, we're going to get the actual shape, which you can see there. So let's see what's going on here. So going back, you'll notice.
See the Windows XP goodness down here?
One slice, we're rotating it around. We need the volume of this slice. Okay?
All right.
So
I won't make you watch any more of this, but that's the idea. And I want to encourage you guys to look through the other videos in that 6.2, 6.3 resources section. The better you can visualize and understand this stuff, the less likely you are to get lost in your calculations, the more likely you are to notice a mistake if you make it. So check out the videos there. They're all really good. They're all things that have helped me deepen my understanding and intuition behind these things. And I want you guys to have that also. That's it for me today, guys. I will see you on Friday. And we need to talk about whether we're doing the work section or integration by parts. I think probably it would be best if I did integration by parts on Friday and then you did work next Wednesday. That'll give you some time to prepare. And there's no harm in that, right? Because they're totally disparate. You don't need one to do the other. So send me what you've got, right? Add in a spring example, and then we can have a meeting sometime between now and Wednesday where you can walk me through how you want to present the material.
Okay, sounds
Alrighty, was that a question from one of my Zoom people, or was that just YouTube barking at me as I close the window? Alrighty, then I will see the rest of you guys on Friday. Take care.